In this video, we're going to look at a bigger theorem. This is the Fermat-Euler Theorem. If you haven't watched the last video, I'd recommend you do that first, as we'll be discussing some ideas from that video in this video. The Fermat-Euler Theorem says, let a and n be co-prime positive integers. Then a to the power of this symbol, this is a Greek letter phi, so a to the power of phi of n, this is some function of n, we'll talk about this in a moment, is congruent to 1 modulo n. A lot to take in here. So first off, we have this word co-prime. We talked about this in the last video. Two integers are co-prime if the only common factor they have is 1. Then we have this statement, a to the power of this mysterious thing here is congruent to 1 modulo n. Let's talk about this symbol here. So this is called Euler's totient function. So what is Euler's totient function? Euler's totient function counts the positive integers up to n that are co-prime to n. I'm actually going to jump here and let's start with phi of 6 just to help us understand what this means. The first thing we're going to do is we're going to list all the integers up to n. So in this case, n equals 6. And the integers up to n are 1, 2, 3, 4, and 5. Now we need to see which of these numbers are co-prime to n, co-prime to 6. Is 5 co-prime to 6? Well, the factors of 6 are 1, 2, 3, and 6. The factors of 5 are 1 and 5. Remember, two numbers are co-prime if the only common factor is 1. Now, the only common factor here I can see is 1. There's no 5 here, there's no 2, 3, 6 here. So 5 is co-prime to 6. I'm going to circle it to say that we know it's co-prime. How about 4? Well, the factors of 4 are 1, 2, and 4. If we look at the factors of 6, we see that we've got a 2 in common. So there's a factor in common that isn't just 1. So 4 is not co-prime to 6. Now 3, we also have a common 3 in the factors of 3 and 6. So these are not co-prime. What about 2? 1 and 2 are the factors of 2. We've got a 2 as a factor of both 2 and 6. So again, these are not co-prime. And finally, we go to 1. If you read this final statement here, 1 counts as being co-prime to n always. Maybe this makes sense to you anyway. I guess if you were thinking about 6 and 1, the factors of 1 are just 1, the factors of 6 are all these things. It's still true that the only common factor that the two have is 1. Obviously 1 doesn't have any more, so it's a bit of a strange statement to say, but 1 will always count as being co-prime to our number. So 1 also counts. So we have two numbers that come before 6 that are co-prime to 6. That means that phi of 6 is equal to 2. Now, I've just realised I'm going to be a little bit more precise with my wording, and it will be interesting in itself to see why I'm doing this. I'm actually going to say we're counting the positive integers up to n, and up to is a little bit ambiguous, and actually what would be better for me to say is up to and including n. So this is a bit of a lesson for all of us to be a little bit careful on our wording here. So I really should have written a 6 here. I'll tell you why I should have done that in a moment. One of the reasons I didn't do that is, well, 6 is definitely not co-prime to 6. 6 and 6 share all of these common factors. So 6 will not count. So phi of 6 is still 2. And that is in general true of pretty much every number, that the number will not be co-prime to its same number. The one exception here is actually 1. Before I wrote that, it was a little bit ambiguous if we're counting any numbers at all, but now we're up to and including 1, we can write 1 here as a consideration. So now we consider, is 1 co-prime to 1? Well, we have this statement here. 1 counts as being co-prime to n always. So that is also true when n equals 1. So that is indeed a number that is co-prime to our n here. Phi of 1 is 1. So this little addition here just helps with the case of phi of 1, as it makes it clear that we should consider 1. Considering the number itself doesn't actually make a difference in all other cases. Let's look at phi of 2. The numbers up to and including 2 are 1 and 2. 1 is co-prime to 2, and 2 is of course not co-prime to itself. So phi of 2 is 1. Let's have a look at phi of 3. So the numbers up to and including 3 are 1, 2, and 3. 1 is co-prime to 3 based on our statement here. 2 is also co-prime to 3. 3 is not co-prime to 3. They're both divisible by 3. So phi of 3 We've circled two things, so phi of 3 is equal to 2. Phi of 4, so let's write all the numbers up to and including 4. Factors of 4 are 1, 2 and 4. We know 1 is going to be coprime. 2 has the factors 1 and 2. We have 2 in common with 4, so that's not coprime. 3, we have a 1 and a 3 as factors. The only thing in common is the 1, so that is coprime to 4, and 4 is not coprime to itself. So phi of 4 is 2. Phi of 5, 1 will be coprime to 5, 2 has factors 1 and 2, definitely coprime to 5, 3 has factors 1 and 3, coprime, 4 has factors 1, 2 and 4, only thing in common is the 1, so that's coprime, 5's not coprime to itself. Phi of 12, okay, this is a bit of a longer one, of course we count the 1. Well, let me put the factors of 12, we have 1, 2, 3, 4, 6, 12. 2 has factors 1 and 2, not coprime. 3, factors 1 and 3, the 3's in common, not coprime. 4 has got a factor 2, not coprime. 5, that's coprime. 5's only got factors 1 and 5, no overlap other than the 1. 6, definitely not coprime, 2 and 3 in common. 7, that's coprime. 8 has a factor of 2, not coprime. 9 has a factor of 3, not coprime. 10, factor of 2, not coprime. 11 is prime, so it's only got factors 1 and 11, so that is coprime to 12. And then 12 is not coprime to itself, of course. So we have 1, 2, 3, 4, so phi of 12 is 4. Before we do this more scary looking one, let's think about phi of p, where p is prime. Let's see what we have for prime numbers already. So we had phi of 2, 2 is prime, phi of 2 was 1, phi of 3 was 2, phi of 5 was 4. Feel free to pause the video and have a quick think. How I can write phi of p in terms of p. Can you spot a pattern with these primes? P is prime, so the only factors of p are going to be 1 and p. For this function, we're considering all the numbers up to and including p. So we're going to be considering like 1, 2, 3, all the way up to p. Now, all of these numbers will have 1 as a factor, but they can't possibly have p as a factor because p is bigger than these numbers, and p has no other factors. So the 1, the 2, the 3, all the way up to p minus 1, they will all be coprime to p. P won't be coprime to itself as it shares the factor p. But none of these can possibly have factor p because p is bigger than these numbers. So the only common factor all these numbers have with p is just 1. So phi of p is p minus 1. A nice little formula. In this case, for example, phi of 31, 31 is a prime number, so I know straight away that phi of 31, so the Euler's totient function of 31 is 30. So that's sort of kind of neat. If you're interested in this, you might want to have a think about what phi of p squared would be if p was a prime, or phi of p to the k, or phi of 2 primes multiplied together. So that's a little bonus task for you, but we won't go over that today. Okay, let's use our newfound knowledge and this theorem to answer some questions. Here we want to find 7 to the power of 8 modulo 10. Now, I'm looking at this and I'm thinking that 7 and 10 are coprime positive integers. The factors of 7 are 1 and 7, and the factors of 10 are 1, 2, 5, and 10. The only thing they have in common is the 1, so 7 and 10 are coprime. That means we can use this theorem. This theorem tells us that A, in this case, let's say A is 7, and let's say N is 10. By this theorem, 7 to the power of phi of 10 is congruent to 1 mod 10. Okay, what is phi of 10? Let's work this out separately. Let's go through and work out which numbers up to and including 10 are coprime to 10. We have 1, by our rule that 1 is always coprime to our number. 2 is not coprime to 10. 10 has a factor of 2. 3 is coprime. 4 is not coprime. 4 is a factor of 2, as does 10. 5 is not coprime, factor of 5. 6 not, because of the factor of 2. 7 is. 8 isn't, because of the factor of 2. 9 is. So we have 1, 2, 3, 4. So we know that phi, maybe I'll write it here, phi of 10 equals 4. So that means by the Fermat-Euler Theorem, 7 to the power of phi of 10, which is 4, is congruent to 1 mod 10. We love this as multiplying things by 1 is super easy. So in this case, we're looking at 7 to the 8. This is 7 to the 4 times 7 to the 4. So I could also write that maybe as 7 to the 4 squared. And we know that is congruent to 1 squared, or 1 times 1. So it's congruent to 1 squared mod 10, which is just equal to 1. So we know that 7 to the power of the 8 mod 10 is congruent to 1. So this little trick here has sped things up for us here. Let's try another one. So here we've got 31 to the 5 mod 12. First thing I'm thinking, 31 and 12, well, 31 is prime, so 31 and 12 are definitely going to be co-prime positive integers, which means we can use the Fermat-Euler Theorem. I'm going to say let our A be 31 and let our N be 12. By the Fermat-Euler Theorem, 31 to the 5 of 12 is congruent to 1 modulo 12. What is phi of 12? We had that before. We said that phi of 12 was 4. By the Fermat-Euler Theorem, 31 to the power of 4 is congruent to 1 mod 12. Now we're evaluating 31 to the power of 5. So 31 to the 5 is the same as 31 to the 4 times by 31, which we know is congruent to 1, based on this here, times 31 mod 12, which is equal to 31. 31 is a bigger number than 12, so in modulo 12 world, we would try and reduce that. So let's think multiples of 12, we have 12, 24. So the remainder here, so if we're thinking on our 12-sided clock, at the top would be 24, and then to count round to 31 would leave us with 7. So that will be congruent to 7 mod 12. So we still had a little bit of calculating to do here, but again, this sort of helps speed things up, knowing that 31 to the 4 was 1. So this is another really useful tool that can help speed things up when we're doing modular arithmetic calculations. You just need to check that our A and our modulo n are co-prime, and then you also need to find out what this totient function of n is. Something interesting to note is last time we looked at Fermat's little theorem. So Fermat's little theorem said if p is prime and a is co-prime to p, then a to the p minus 1 is congruent to 1 mod p. Now, maybe you'll notice some similarities between these two theorems. If we consider this top theorem and make n a prime number, then we would have a to the phi of p being congruent to 1 modulo p. Now the phi of p, we said here, was p minus 1. So if we were to plug that in here, when n is a prime, we would have a to the p minus 1 being congruent to 1 modulo p, which is exactly what Fermat's little theorem says. So Fermat's little theorem is a special case of the Fermat-Euler theorem for when n is a prime number. I hope you enjoy using both of these tools to help you with modular arithmetic questions. Thanks for watching. I hope you enjoyed this video. If you want to see more aesthetic mathsy videos, do check out my channel and subscribe.